Welcome to the lecture number 46. In this lecture we are going to study how to design the synchronous counters. It will be up down counter or up counter or down counter or modulus counters. So if you want to design the synchronous counter, we should have a prerequisite or prior knowledge related to the excitation table of flip-flops. So we'll see why we require excitation table for each flip-flop. Once you get to know about the excitation table of each flip-flop, then we can design the synchronous counters. Now we will see what is meant by excitation table of a flip-flop. If you define clearly, your excitation table gives you inputs required to be applied to the flip-flop to take it from present state to next state. Suppose you want to move from 0 to 1 or 1 to 0, what input one should apply so that your flip-flop will change its state. So for each flip-flop we have a predefined transition 0 to 1, 0 to 0, 1 to 0 or 1 to 1. So for those transitions we should have a predefined inputs under which condition a flip-flop will move from one particular state to another particular state. So that table is called excitation table. So this excitation table we can easily construct by using the truth table. Now we will try to construct the excitation table for each flip-flop. So before going to the excitation table, so let us recap the difference between asynchronous and synchronous. If you look at here, this is the asynchronous counter which we already designed. So in all the case what we did is we kept j equals to k equals to 1 and use the toggling action for the counting action. And your output of the previous flip-flop will act as a clock to the second flip-flop. Okay. In case of synchronous counter, your clock is given to all the flip-flops directly. Okay. So in this case, for each clock cycle, if you keep j equals to k equals to 1, each clock, all the flip-flop will toggle. That means all zeros to all ones to all zeros, again all ones to all zeros to all ones. That means, so if you use the same as your, procedure as your previous asynchronous counters, for the synchronous counter you are not going to do any counting action. It will be toggling between all zeros to all ones to all zeros. If you keep j equals to 1 and k equals to 1 and k, if you apply clock simultaneously to all the flip-flops. Okay. To avoid this problem, we are not going to connect j equals to 1 and k equals to 1. We are going to design a circuit for j and k for each flip-flop. For each flip-flop, what should be the j input and what should be the k input. Please remember, this is a major difference. In case of asynchronous counters, we always connect your j equals to 1, k equals to 1 and you apply the clock. Whereas in case of synchronous counters, you cannot do that way. You have to manually design each input circuit. For flip-flop 1, what will be the j1, k1. For flip-flop 2, what is the j2, k2. Similarly, for flip-flop 3, what is the j2 and j3 and k3. So that means we need to know the jk flip-flop excitation table. If you want to study of this particular flip-flop, how this output going to change depending on our requirement, we should know what input we should give for this flip-flop. Similarly, for the second flip-flop, if it wants to change from 0 to 1 or 1 to 0, we should define what should be the j2 and k2. Similarly for j3 and k3. That's why we require a excitation table for each flip-flop, whether you are using a T flip-flop or whether you are using a JK flip-flop. This is a major difference between your asynchronous and synchronous, where you are going to define circuit for each flip-flop inputs, and we are no more going to use j equals to 1 and k equals to 1 for the synchronous counter. So let us see how we are going to get the excitation table for each flip-flop. We'll start with JK flip-flop first. So let's take JK flip-flop truth table first. So you're going to have J and K, and you're going to J, K and previous output and next output. So if you take J equals 0, K equals 0, the previous output is 0, it will be in the same state. For the same condition of J equals 0, K equals 0, the previous output is 1, it's going to be in the same memory state. Similarly, when j is 0, k is 1, the previous output is 0. It's going to be in the 0 because when k equals 0, your output is supposed to be in the reset state. Similarly, when j equals 0, k equals 1, the previous output is 1. It's going to reset to 0. Now if j equals to 1 and k equals 0, the previous output is 0. It's going to set to 1 state. Similarly, if j equals to 1 and k equals 0, the previous output is 1. It will be in the same set state. If both are 1 1, j and k are 1 1, the previous output is 0. It's going to toggle to 1. And both are 1 1 again. If the previous output is 1, is going to toggle to 0. So this is the truth table of your j and k flip-flop. If you observe carefully, this is your jk flip-flop truth table. Everybody knows. Now I am going to construct the excitation table for the jk flip-flop. Now if I want to change my output, previous output to next output to 0, that means 0 to 0 transition. If you observe here, this is 0 to 0 transition, and this also 0 to 0 transition. That means if you look at here, your j is same, whether k is 0 or 1, it is going from 0 to 1. That means you can keep 0 and x. That means 0 0 will give you the same transition, and 0 1 also will give you the same transition. Now we'll make 0 to 1. So if you look at here, this is 0 to 1 transition. This is also 0 to 1 transition. So if you look at here, in this case your j equals to 1, j equals to 1. But if you look at here, k is changing from 0 and 1. That means 1 0 and 1 1 both is giving a transition from 0 to 1. That means I can write it as 1 comma x. So it doesn't matter what is the k value, whether it's 0 or 1. When you are having j equals to 1, it's going to change your flip-flop output from 0 to 1. Now I am going to take 1 to 0 transition. So if you look at here, 1 to 0, this 1 to 0 transition, this also 1 to 0 transition. If you look at here, 1 to 0 transition, your k is 1, your k is 1, but your j is changing 0 and 1. That means, so whenever you want to change your output from 1 to 0, you require k equals to 1. J can be anything, it can be 0 or 1. That means x comma 1. If I want to move from 1 to 1, so if you look at here, your 1 to 1 is here and your 1 to 1 is here. In both the cases, if you look at here, your k is 0 in both the cases, but your j is changing. If you look at here, your j is changing 0 to 1. That means you can write it as x comma 0. So this is your excitation table. Please remember, this will be very useful for designing the synchronous counters. Hope it is clear. You just simplified your truth table to a simplest form where you can directly define. Whenever I want 0 to 0 transition, I can keep j equals 0, k can be anything. Similarly, if I want to make a jk output from 0 to 1, I can keep 1 comma x. That means 1 1 can give the same transition, or 1 0 also will give the same transition. Similarly, 1 to 0, x comma 1, and 1 to 1 will be x comma 0. So this is the excitation table for jk flip-flop. Now we'll see the t flip-flop in a moment. Now let's take the t flip-flop truth table. So you are going to have t, your qn and qn plus 1. When t is 0, the previous output is 0, it will be in the same state. If t is 0, the previous output is in one state, it will be in the same state. If t is 1, the previous output is 0, it toggle to 1. If t equals to 1, if the previous output is 1, it toggle to 0. So these are the So this is the truth table for the T flip-flop. Now we are going to construct the excitation table for T flip-flop. So that means you are going to have Qn, then Qn plus 1 and required T input. Let's make 0 to 0 transition. For a T flip-flop, if I want to move from 0 to 0, okay, what type of input I am supposed to? If you look at here, 0 0 transition is giving T equals 0, and 0 to 1 T equals to 1, then 1 to 0 1, and 1 to 1 0. This is the excitation table for T flip-flop. Now we'll see the excitation table for D flip-flop. So first we'll see the truth table of D flip-flop. D, Qn and Qn plus 1. When D is 0, if the previous output is 0, it will be in the same state. If D is 0, if the previous output is 1, it goes to 0 state. If D is 1, if the previous output is 0, it goes to 1 state. If D is 1, if the previous output is 1, it will be in the same state. So this is your D flip-flop truth table. Now I am going to construct the excitation table for D flip-flop. So this is my previous output and this is my next output and required D input. So 0 to 0 transition you require D equals 0. 0 to 1 transition you require D equals to 1. 1 to 0 transition you require D equals 0. 1 to 1 transition you require D equals to 1. So this is the excitation table for the D flip-flop. Now we will try to construct the SR flip-flop excitation table. Let's take S, R, Q and Qn plus 1. 0 0. The previous output is 0, it will be in the same state. 0 0. The previous output is 1, it will be in the same state. 0 1. If the previous output is 0, it will be in the reset state. And 0 1, if the previous output is 1, it reset to 0. And 1 0, if the previous output is 0, it will set to 1 state. One 0, if the previous output is 1, it will be in the same 1 state. And if S and R are 1 1, you don't care about the output, don't care. Similarly, if the previous output is 1, again don't care. So this is the truth table of SR flip-flop. Now I am going to construct the excitation table for SR flip-flop. So this is Q and Qn plus 1, and let me take my S and R inputs. So if I want to move from 0 to 0, so this is 0 to 0, this also 0 to 0. So 0 to 0 transition, if you look at here, this is S is 0 in both the places, but R is changing to 0 to 1. That means I can write as 0 comma X will give you the transition from 0 to 0. Let's take 0 to 1, 0 to 1, so 0 to 1 it takes 1 comma 0, then 1 to 0, 0 comma 1, 1 to 1. Look at here, 1 to 1, this also 1 to 1. So in this case your R is 0, but your S is changing 0 to 1 here. That means I can write it as X comma 0. So this is a excitation table for SR flip-flop. So we don't consider this input combination and transition also, because this is a invalid input combination. So we will build our excitation table only from till this table only. So this is your SR exit. Now we are familiar with the excitation table. Now we are going to design the synchronous counters. Before that, let me explain what is the procedure one should follow when someone wants to design a synchronous counter, depending on our interest. It may be up counter or down counter or any mod counter. Now we'll see how to design the synchronous counter. So these are the steps one should follow when you want to design a synchronous counter. Step number 1 is you need to define how many number of flip-flops are required for the given operation. Suppose you are counting from 0 to 7, you require minimum 3 flip-flops. Suppose you are counting from 0 to 15, you require minimum 4 flip-flops. So this is the first thing you are supposed to do. Based on your counting number, you decide how many flip-flops you are required. Next step, you are going to draw the state diagram. State diagram is nothing but for each clock cycle, what is the state of the flip-flop. Suppose you take a 0 to 3 counter. In the first state, both the flip-flops will be showing 0 0. In the next state 0 1. In the next state 1 0. In the next state 1 1. So these are the 4 states that you are supposed to draw a simple diagram how your flip-flop output states are changing for each clock cycle. Once you know the state diagram, then you write the state table. For each flip-flop, what is the previous output, what is the next output. Once you clear with the state table, you choose the which flip-flop you want to use, whether you want to use a T flip-flop, whether you want to use a D flip-flop or a JK flip-flop. Once you clear with the flip-flop selection, then construct the excitation table. From the state table, you construct the excitation table for each flip-flop and their output transition. What should be the input for that particular flip-flop? Once you get the table, then you can form the K-map for each flip-flop input. Suppose you are using a T flip-flop, what is the input circuit for the T1, and similarly what is the input circuit for the T2. Once you get the expression, and draw the logic diagram and apply the clock to all the flip-flop, then you will get the required counting operation, whichever the way you defined it. Now let's take the simple example and try to show you all the 6 steps which I will follow for designing a synchronous counter using flip-flops. So now let us construct or design the synchronous counter. Let's take a simple example problem. The question will be asked something like this: design synchronous counter which can count 0 to 3. So this is the problem statement. So you will be given exactly in the similar fashion: design a synchronous counter which count from 0 to 3 or 0 to 10 or 0 to any arbitrary number. Now you are clear with the problem. Now step number 1. In step number 1, you are supposed to define how many flip-flops do you require for this operation. So from 0 to 3 counting, you require minimum 2 flip-flops. So 2 flip-flops are required. Once you define the number of flip-flops required, now step number 2 is you need to draw the state diagram. State diagram means your flip-flop first will start at 0, then goes to 1, then goes to 2, then goes to 3, and 3 to 0. This is your state diagram in a decimal form. So if you define the binary form, so your flip-flop will start at 0 0, then it goes to 0 1, then goes to 1 0, then goes to 1 1, then 0 0. So this is your state diagram for your counting sequence. So here this bit will be stored by flip-flop number 1 and this bit will stored by flip-flop number 2. So indirectly your state diagram gives how your 2 bits are storing in the selected flip-flop, how their output is changing for each clock pulse. So this is a state diagram. Now we will make the state table, that is your step number 3. In state table, what you are going to do, you have to take the present state of the flip-flops and next state of the flip-flop. So present state of the flip-flops and next state of the flip-flops. So if I take present state of the flip-flops, let's take flip-flop output as Q0 and Q1. This is flip-flop number 1, this is flip-flop number 2. 0 0. If it is 0 0, in the next clock pulse goes to 0 1 state. This is your Q0 and this is your Q1. If the flip-flop in the 0 1 state goes to 1 0 state based on your state diagram. Please remember, I am making my state table. This is a state table. The state table can be constructed from the state diagram. When it is 0 0, next state will be 0 1. If it is 0 1, it goes to the 1 0 state. If it is 1 0, it goes to 1 1 state. If it is 1 1, it goes to 0 0 state. This is called state table. Now we will take the step number 4. Step number 4 is selection of flip-flop. So I'm going to, in step number 4, you are going to select the flip-flop for this operation. So I'm going to select T flip-flop for my circuit. I am selecting T flip-flop. Once you select the T flip-flop, now you have to design the excitation table for the given operation. That will be your step number 5. In step number 5, you are going to design the excitation table. So for designing excitation table, you require state table. That means again you have to consider your present state of the flip-flop, next state of the flip-flop, then required inputs. Required input to be applied to flip-flops. Now we'll try to see how you are going to do that. So this is very important step for the, so please remember, let's say my present state, this is my Q0 and Q1, similarly Q0 and Q1. If it is 0 0, it is going to be 0 1 state. Now we have 2 flip-flops here, T1 and T0. So T0 is related to Q0 output and T1 is related to the Q1 output. Let me make it prime. Let me make it prime here. Or let me make it star. So this is nothing but your next states. So if you observe carefully, your first flip-flop, your first T flip-flop is changing from 0 to 1. So for a T flip-flop, if you remember the excitation table, so you should know the excitation table to construct the excitation table for the counter. So 0 0 will be T0, 0 1 will be 1, 1 0 will be 1, 1 1 will be 0. So this is the output transition and this is a required input for the T flip-flop. If you look at here, your Q0 is changing from 0 to 1. In that case, your T0 should be 1 and T1, if you look at the T1 output, it is going from 0 to 0. 0 to 0 0 transition require T equals 0 only. Now let's take 0 1. 0 1 going to change to 1 0. If you look at here, if 1 is changing to 0, 0 is changing to 1. That means your T0 should be 1 input and T1 also should be 1. In the next state will be 1 0. It goes to 1 1 state. In this case, your Q0 is changing from 0 to 1. That means your T0 should be 1. Whereas your Q1 is in the same state. That means your T should be 0. And if it is in the 1 1, it goes to 0 0 state. In this case, your T is changing to 0. This T also, your Q0 also changing to 0. Your Q1 also changing to 0. That means you require T0 should be 1 and T1 should be 1. Then only this transition will take place. Please remember, design the circuit for T1. You are going to design one circuit for T1 and another circuit for T0 by using a simple K-map method. Let's take your T1 K-map. You are having 4 inputs. You are having 2 inputs. That means you can use 2 variable K-map. So if you observe carefully, this will be, this is your Q1 and this is your Q0 bar, Q0 and Q1 bar and Q1. So if you feel carefully, 0, 1, 0 and 1. Similarly, if you feel for T2, same thing, your Q1 bar as input. This is your Q0 bar and this is your Q0. Now it will be 1, 1, 1 and 1. This is your T0. Now if you take T0 you can form 1 quad. So T0 will be 1. That means your T0 always connected to the 1. And similarly, if you look at here, T1, if you take a pair here, T1 always connected to Q0. So please remember, these are 2 important things we concluded. First thing is 0 to 1, 1 to 0, 0 to 1, 1 to 0. Your T0 must always connected to 1. And similarly, if you take the second T flip-flop, for the given transition, you should connect your Q0 as an input to the T1 flip-flop. Then only your desired counting operation will takes place. Now we'll try to construct the circuit and we'll try to see whether it's going to work for us or not. Now it's very clear, you need 2 flip-flops. So take in 2 flip-flops. Since it's a synchronous counter, so I'm going to give clock simultaneously to both the flip-flops. Now if you observe, your T0 should be always given to 1 and your T1 should be given to Q0. That means output of this flip-flop is a input to the second flip-flop. This is my Q1 and this is my Q0 and this is first T flip-flop, that is T0, and this is my second flip-flop T1. Now let us analyze and let us see. So let's take the clock and Q0 and Q1 and Q0. If you look at here, the first clock pulse, let us assume both are 0 zeros. When the first clock comes, your Q0 will toggle because it is given always to 1. Your T flip-flop action is when T equals to 1. For each clock pulse, this first flip-flop will toggle. That means this goes from 0 to 1. And the second flip-flop, if you look at here, your T input is 0 to this flip-flop. When T is 0, it will be in the same state. And the second clock, your T0 flip-flop again will toggle. And second T flip-flop, if you look at here, this previous output is 1. That means your T1 is 1 now. When T1 is 1 and the clock is applied, it toggle to 1. In the next clock pulse, again your Q0 will move from 0 to 1. For this flip-flop, if the previous output is 0, it will be in the same state. In the next clock pulse, your Q0 again toggle to 0. And for this flip-flop, the previous output is again, your T1 is 1, again this will toggle to 1 to 0. If you look at here, your counting is taken 0, 1, 2, 3 and 0. So this is how we can design a synchronous counter using T flip-flops. Now I am going to show the same circuit by using DEET software, and we will try to see whether we are going to get the same or not. Now let us simulate the synchronous counter using T flip-flop. Since we don't get T flip-flop directly from the drop down box, so what I did is I have taken a JK flip-flop and shorted both J and K as a single input. Now this JK flip will act as a T flip-flop. This is one T flip-flop, this is one T flip-flop, and this is another T flip-flop. Now I am going to connect the circuit as per the derivation we did it. That means first T flip-flop is supposed to be connected to 1 and second flip-flop should be connected to the Q of the previous flip-flop. I can see here the first flip-flop, the T0 is connected to 1 and T1 is connected to Q. As usual, this is a preset input for both the flip-flop, and this is a clear input, and this is my Q0 and this is my Q1, and this is my clock. If you observe carefully, the clock is given to both the flip-flop at the same time. Now I am going to run my simulation. So now there is nothing at the output ports. Now let me clear it. Now I cleared. The moment I make clear equals 1, my counter going to start from 0, 1, 2, 3 and 0. You can see here 0 to 1, 1, 0, then 1, 1, then 0, 0. So this is how you can use the T flip-flops for designing synchronous counter. This is for 0 to 3. Now I am going to show you how to extend it to 3-bit, 4-bit in a moment. Now let us design the second problem. Now you are asked to design synchronous counter which can count from 0 to 7. This is your problem. Now we'll start with the step number 1. So to count from 0 to 7, that means all zeros to all ones in binary form, you require at least 3 flip-flops because you need to store 3 bits. That means you require 3 flip-flops. This is the first thing you are supposed to look. Then look for the step number 3, that is a state diagram. State diagram start from 0, then 1, then 2, 3, 4, 5, 6, 7 and 0. So if you write in the binary form, it will be 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1 to 0. So this is your state diagram. For each clock pulse, your output of the 3 flip-flop will move from one state to the other state. Now you are clear with the state table. Now I am going to construct the. Now this is your state diagram. So this is your Q0 and this is your Q1. That means this is your first flip-flop output and this is second flip-flop, and this is your third flip-flop output. The first flip-flop output, second flip-flop output and third flip-flop output. Now you are very clear with the state diagram. Now I am going to make the state table. State table will give you present state and next state, how it is going to be moved. So if I start from state table, so this is my present state and this is my next state of the flip-flops. So I am having 3 flip-flops, Q0, Q1 and Q2. Similarly, next state will be Q2 star, Q1 star and Q0 star. So if it is 0, 0 state, goes to 0, 0, 1 in the next clock pulse. If it is in the 0 0 1 state goes to 0 1 0. If it is in the 0 1 0 state, it goes to 0 1 1 state. 0 1 1 state goes to 1 0 0. Similarly, if it is in 1 0 0 state, goes to 1 0 1. It is 1 0 1 goes to 1 1 0. 1 1 0, it goes to all ones. If it is all one state, it goes to all zero state. This is your present state and this is your next state. Now we are clear with the state table. Now I am going to add step 4 here only. I am going to make step 4. I am going to take T flip-flop for my circuit design. This is my step 4, selection of the flip-flop. Now step 5 is we are supposed to make the excitation table from the state table. So that means you are going to use the same tabular column. Only thing is you are going to add an extra column here. That extra column will have flip-flops. So we require 3 flip-flops, T0, T1 and T2. Now what we are going to do is for Q0 related transition, you are supposed to give the input to the T0. If you look at here, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. So your Q0 is toggling for each clock pulse. That means your T0 always 1. It should be 1 and again 1, again 1, because every time it is toggling. For toggling action, you should keep T should be 1. So your T0 is done, because if you observe carefully, your entire these 8 bits and these 8 bits are complementary to each other. That means toggling. So 0 to 1, 1 to 0. That's why I'm keeping T0 as 1 1 for all the transition from 0 to 1 for all the 8 states. Okay. Now if you look at the T1, if you look at here, this is changing from 0 to 0 means 0. Next 0 to 1 means 1. If you look at here, 0 to 0 means 0, 0 to 1 means 1. Then 1 to 1 means 0. Then 1 to 0 means 1. Then 0 to 0 means 0. And 0 to 1 means 1. Then 1 to 1 means 0. And 1 to 0 means 1. So this is 1 0 1 0 1 0. If you look at the third one, so 0 to 0, 0 to 0, 0 to 0, 0 to 0 and 0 to 1. That means you are going to have 0, 0, 0, then 1, again 1 to 1, 1 to 1, 1 to 1, then 1 to 0. That means again 0, 0, 0 and 1. Now this year, now let's fill the K map for T0. Let's start with T0. T0 all are ones. So all are 1 means you can form a octet. So your T0 becomes 1 always. That means your T0 should be always connected to 1. And if you consider T1, 0 1, 0 1, 0 1, 0 1, 0 1. So if we take a quad here, you are going to get a T1 as Q0. Similarly, if you take T2, it will be 0, 0, 0, 1, 0, 0, 0 and 1. If you take this as a pair, you are going to get T2 as Q0 into Q1. So these are the 3 inputs we are supposed to give to the 3 T flip-flops along with clock. Simultaneously we are going to count 0 to 7. Now we'll try to design the circuit in a moment. Now these are my T0 flip-flop, T1 flip-flop and T2 flip-flop, and I'm going to give clock to all the flip-flops simultaneously. Now as for the K map, your T0 always connected to 1, so that this flip-flop will toggle for every clock pulse. Your second flip-flop input should be comes from the Q0. So this is my Q0 and this is my Q1. This is my Q1. For T2 you are supposed to use a AND gate, and you are supposed to connect your Q0 as well as Q1, and this output I am going to give as a input for the your third flip-flop T2. Now this is my Q1 and this output is my Q2. Now the moment you apply the clock, your Q0, Q1, Q2 will count from 0 to 7. Now we are going to verify the same by using DIT software in a moment. Now let us simulate the 3-bit up counter, or a counter which can count from 0 to 7 in a synchronized fashion. If you observe carefully, my clock is given to all the flip-flops at the same time, and first flip-flop is always given to 1 as per our K map expression. Second flip-flop, your Q0 should be as an input to the second flip-flop. For the third flip-flop, you are supposed to take Q0 and Q1 as a input to the AND gate. The AND gate output should be input to the third flip-flop. That is nothing but Q0 into Q1, and this is my Q0, Q1 and Q2. I have connected to a BCD to 7 segment display, and third bit I connected permanently to 0. So now this display can display 0 to 7 depending on your Q0, Q1 and Q2 values, and as usual clear is connected to all the flip-flops, preset is connected to all the flip-flops. Now I'm going to clear my flip-flop outputs to all zeros. Now let's run the simulation. Now let me make all the flip-flops to 0. The moment I keep my clear to 1, it is going to count from 0 to 7. Just have a look. 1, then 2, 3, 4, 5, 6 and 7 and 0. So this is how you can use a T flip-flops for constructing a synchronized circuit. This is for 0 to 7. We can extend the same circuit to 0 to 15 also. That we will see in a moment. Now let us consider the 4-bit up counter, 4-bit synchronized up counter. You can see there are 4 flip-flops. So till third flip-flop we already constructed. For the fourth flip-flop, what I did is I just connected Q0, Q1, Q2 through a AND gate. If you look at here, this first input is nothing but Q0 into Q1, and your third input is nothing but Q2. That means this output of the AND gate is Q0, Q1, Q2. This will act as a input to the fourth T flip-flop. Okay. This you do it at your own time, how to get this expression for the fourth flip-flop, because till 1, 2, 3 we already did it, so you can take it granted. Fourth one you have to do it manually. For the time being we assume it is already derived. Fourth flip-flop input should be Q0, Q1 into Q3. Fourth flip-flop input. Now let us consider the 4-bit synchronized up counter. Everything is same till third flip-flop. Fourth flip-flop there is a small extra circuit added. The fourth flip-flop we added for the fourth bit, and fourth flip-flop input is defined as Q0, Q1 and Q2. This will be derived from the same process which I followed till now. For the timing I am assuming I already derived it. I am found out that fourth flip-flop input should be Q0, Q1 and Q2. So you can look at here, this is Q2, and if you look at here, this is AND gate. This AND gate is nothing but Q0 into Q1. So I am going to test my circuit. First let me clear it. Let me run the simulation. So let me preset to all ones, then let me preset to all zeros. Let me clear all the flip-flops to 0 0. The moment I make my clear equals to 1, it's going to count from 0 to F. You can clearly see your binary equivalent also changing, at the same time your decimal equivalent also changing in the BCD to 7 segment display. So this is how we can construct the synchronized up counter using T flip-flop. Now you are going to see how to design the down counter using the T flip-flop in the same fashion. So now let us design the down counter using T flip-flop. Now the question will be design synchronous down counter which can count from 0 to 3, or we can say simply 2-bit up counter. Now let us see how to design the 2-bit up counter. So step number 1, since we need to count 0 to 3, we need at least 2 flip-flops. Step number 2, you need to form the state table. In step number 2, you need to form the state diagram. In state diagram, we will start from 0. When you give the next clock pulse, it goes to 1 1 since it's a down counting. Then 1 1 2, 1 0, 1 0 2, 0 1, and 0 1 2, 0 0. This is a state diagram, or if you want to represent the binary form, 0 to 3 and 3 to 2, 2 to 1 and 1 to 0. This is your state diagram. In step number 3, I am going to form the state table. So present state of the flip-flops and next state of the flip-flops. So if you consider both 0 0, just let's take Q0, Q1 flip-flop outputs, and this is a Q0 star next state and Q1 star next state. When both are 0 0, it's going to the 1 1 state. When 0 1, if you look at here, when it's 0 1, in the next clock pulse is going to 0 0 state. If it is 2 1 0, it is going to 0 1 state. If it is 1 1, it is going to 1 0 state. Now your state table is ready. Now step 4, I am considering the T flip-flop for this work. Now I am going to consider the step number 5. Step number 5, I am just going to extend the same state table, and I am going to write here required input for T0 and T1. So I am making my excitation table by using the state table. So if you observe carefully, your Q0 is toggling 0 to 1, 1 to 0, 0 to 1 and 1 to 0. That means for each clock pulse your T0 should be always 1. Then only this toggling action will take place, 0 to 1, 1 to 0, 0 to 1, 1 to 0. So all ones. Look at your T1, 0 to 1, you need T equals to 1, 0 to 0, you need T equals 0, 1 to 0, you need 1, and 1 to 1, you need 0. So here I am using the T flip-flop excitation table. T flip-flop excitation Q1 plus 1, and T, if you write here 0 to 0 you require T, 0 to 1 you require 1, 1 to 0 you require 1, 0 to 0 you require 0. So this is a T flip-flop excitation table I have used here. For the Q0, all the time your Q0 is toggling, so that's why I am keeping T0 1 in all the 4 cases. Whereas in case of Q1, 0 to 1 you need 1 as per the excitation table, 1 to 1 you need 0 because it should be in the same state. Now we are going to make one K-map for T0 and one more K-map for T1. So this is my Q1 bar, Q1, Q0 bar, Q0. Similarly Q1 bar, Q1, Q0 bar, Q0. Now if you fill the T0 it all ones, so I can take my T0 as 1. That means your T0 is permanently connected to the power supply or logic 1. And if you fill the T1, 1 0 1 0, you can form a pair here. Your T1 is permanently connected to Q0 bar. So if you observe carefully with the up counting your T0 is same. So if you look at here, for the down counting case, previously it was Q0, now it become Q0 bar. So that means you can easily extend it to 3-bit, 4-bit by simply changing your next flip-flop input to, instead of Q0 bar, instead of Q0 into Q1 to Q0 bar into Q1 bar for the 3-bit, similarly for the 3-bit also. Now if you construct the circuit for this, you are going to have 2 flip-flops, the T flip-flop 1, T0, second T flip-flop T1, clock is given simultaneously, and this T flip-flop is connected to always 1, and this Q0 and this your Q1, your Q0 always connected to T1 flip-flop. Now my Q0, Q1 going to count in the downwards direction 0, 3, 2, 1 and 0. That we are going to verify in a moment using DEED software. Now you can see here, this is a down counting circuit, down counting synchronous circuit. You can see that clearly the difference is only one thing, where your Q bar is connected as input to the JK flip-flop. Rest all are same. Your first flip-flop is connected to 1 permanently. Okay, let's run the simulation. Let's clear all the flip-flop outputs to 0, 0. The moment I make my clear equation, it's going to count 3, 0 to 3, 3 to 2, 2 to 1 and 1 to 0. Let's check 0, then 3, then 2, then 1, then 0. So this is your down counting with only 2-bit. If it is a 3-bit, what you are going to do? You are going to add one more extra flip-flop here. This will be same. For the third flip-flop, you are supposed to give the input to J and K. That will be multiplication of Q0 bar and Q1 bar through a AND gate. That AND gate output will be given as a input to the third flip-flop. If you look at the circuit, so the same thing can be derived by using all the steps whatever we followed till now. Since it is just opposite of your up counting, so everything is same. Only difference is your Q0 bar is connected as input to the second flip-flop. For the second flip-flop, previously it was Q0 into Q1. This time it is Q0 bar into Q1 bar. The same thing through a AND gate is given as input to the third flip-flop. If I run this circuit, it is going to count in the downwards direction. Let's clear it and let's run it. Now you can see clearly 7, then 6. So it is counting in the downwards direction. So similarly, we can extend it to 4-bit. If you have extended 4-bit, you are going to take one more flip-flop. For this flip-flop, you are going to take one AND gate. For this AND gate, you are going to give Q0 bar into Q1 bar into Q2 bar as an input. That output of the AND gate is given as a input to the fourth flip-flop. That is going to count 0 to F. So this is all for up counting and down counting with the T flip-flop. In the next lecture, I am going to show you how to design the up counting and down counting with the JK flip-flop, then up down counter in the same circuit like what we did it for the asynchronous mode. Thank you all.